June 14, 1942, North African desert, 50 kilometers west of Tobruk. The morning sun cast long shadows across the barren landscape as Lieutenant Harold Winters squinted through his binoculars. His supply convoy, 30 trucks carrying ammunition, fuel and water, had to cross 20 miles of open desert to reach British 8th Army positions. German reconnaissance planes had been spotted at dawn. The dust trail behind the convoy stretched for miles. No matter how slowly they moved, the vehicles kicked up plumes of fine sand that hung in the still desert air. From above, it might as well have been a flashing signal light. Lieutenant Winters lowered his binoculars and climbed back into the lead vehicle. "They'll spot us within the hour," he told his driver, "and then the Stukas will come." The convoy pressed forward, the growl of engines echoing across the empty landscape. Every man knew the routine by now. Once spotted, they would scatter, using whatever natural depressions they could find for cover. It was never enough. In the past month alone, 3 similar convoys had been decimated by German air attacks. In the 7th truck from the front, Dr. Reginald Sutton sat hunched over a worn notebook. Unlike the soldiers around him, Sutton wore civilian clothes, khaki trousers and a light cotton shirt, both covered in chemical stains. A Cambridge-educated chemist, he had been transferred to North Africa after his work on smoke compositions had drawn the attention of British High Command. The truck jolted over a rock, causing Sutton to smudge his calculations. He frowned, erased the error, and continued working. The numbers were promising, but he needed more time. Time was precisely what they didn't have. The radio in the lead vehicle crackled to life. Enemy aircraft approaching from the north. Estimated 3 minutes until visual contact. Lieutenant Winters gave the order to disperse. The convoy broke formation, vehicles fanning out across the desert floor. Dr. Sutton barely noticed the change in direction. He was too absorbed in his work. Fingers stained with chemical compounds, mind racing through molecular structures and reaction rates. The distinctive whine of diving Stuka bombers filled the air. The North African campaign had become a logistics nightmare for Allied forces. The vast distances between supply bases and front lines meant that everything, ammunition, fuel, water, medical supplies, had to be transported across exposed terrain. German air superiority made these convoys prime targets. Standard operating procedure involved camouflage netting, movement at night, and dispersion tactics when under attack. None proved consistently effective. The desert environment offered few natural hiding places, and the heat made night operations extraordinarily difficult for men and machines alike. The British Army had experimented with smoke screens as early as 1940, deploying them to conceal naval bases and strategic installations during the Blitz. Hexachlorothane smoke generators produced thick white clouds that could mask large areas from aerial observation. But these systems had critical flaws in mobile operations. The smoke dispersed too quickly in open terrain, required massive amounts of material for sustained coverage, and often gave away positions due to the distinctive deployment pattern. Dr. Reginald Sutton had studied these problems extensively. Before the war, he had specialized in polymer chemistry at Cambridge University, focusing on industrial applications for new synthetic materials. When war broke out, his expertise was redirected to defensive technologies. After 18 months working on various chemical compounds in a London laboratory, Sutton had developed a theory. Traditional smoke screens failed in desert conditions because they relied on particulate matter that couldn't remain suspended in the hot, dry air. His solution involved a 2-stage chemical reaction that would create a colloid, microscopic particles suspended in gas, that would be heavier than standard smoke, more persistent in adverse conditions, and could be controlled more precisely. The War Office had dismissed his initial proposals. The chemical components required were too exotic, the deployment system too complex for field conditions. But as convoy losses mounted in North Africa, Sutton's ideas received a second look. He was attached to the 7th Armoured Division as a technical observer, given a small workshop in Alexandria, and told to develop a working prototype. For 3 months, he had tested various formulations, each failing under actual desert conditions. The mixtures either dispersed too quickly, required impractical quantities of precursor chemicals, or created toxic byproducts that endangered the very troops they were meant to protect. The convoy attacks continued, with loss rates approaching 40%. Every failed experiment meant more supplies destroyed, more men killed. Sutton worked through nights, barely sleeping, driven by the knowledge that every day without a solution meant dozens more lives lost. His breakthrough came from an unexpected source, not from his chemistry training, but from his childhood in the foggy valleys of rural England. 1 week before the convoy mission, Dr. Sutton had been standing outside his workshop, watching distant naval vessels disappearing into the natural morning fog over Alexandria harbour. The way the fog clung to the water's surface, resistant to the strengthening sun, triggered a memory. As a boy in Yorkshire, he had observed how morning mists behaved differently depending on the season. In summer, they burned away quickly under the sun's heat, but in autumn, when the ground was cold and damp, while the air above remained relatively warm, the fog would persist for hours, clinging to the landscape. This temperature differential created a boundary layer that trapped moisture particles. What if he could artificially create such conditions in the desert? Not with water, that was far too precious a resource, but with his chemical compounds. Sutton returned to his workshop and worked through the night. By morning, he had outlined a radical new approach. Instead of trying to create a single component smoke that would inevitably dissipate in desert conditions, he would develop a 2-stage system that mimicked the physics of natural fog formation. The first stage would be a cooling agent released at ground level, a mixture of calcium chloride and compressed carbon dioxide that would rapidly lower the temperature of the air immediately above the desert floor. The second stage would be an aerosolized polymer solution that, when released into this artificially cooled layer, would form a semi-stable colloid resistant to dispersal. In theory, this would create a dense, ground-hugging fog that would be far more persistent than conventional smokescreens and could be deployed from moving vehicles. The risks were substantial. The chemicals required were corrosive and potentially hazardous if mishandled. The cooling component could cause frostbite if personnel came into direct contact with it. Most concerning was the untested nature of the system in actual combat conditions. Laboratory tests could only approximate the chaotic environment of a battlefield. Furthermore, Sutton was violating multiple protocols by developing this system without full approval from the Chemical Warfare Directorate. His authorization extended only to modifications of existing systems, not the creation of entirely new ones. If his experiment failed catastrophically, caused casualties among British forces, or proved ineffective during an actual attack, he would face severe consequences. Despite these risks, Sutton convinced Lieutenant Winters to allow a field test during the next scheduled convoy run. With minimal equipment and makeshift apparatus assembled from spare parts, Sutton prepared 12 deployment units. Each consisted of a modified fire extinguisher containing the cooling component and a connected sprayer system for the polymer solution. The units were installed on every third vehicle in the convoy, with simple mechanical triggers that could be activated from inside the cab. The system was crude, improvised, and entirely untested in combat conditions. It represented both the best hope for the convoy's survival and a potentially career-ending gamble for the civilian scientist. On the morning of June 14th, as the convoy prepared to depart, Sutton provided hasty instructions to the drivers of the equipped vehicles. The men exchanged skeptical glances. They had seen experimental systems fail before, often with lethal consequences. As the convoy moved out into the open desert, Sutton made final adjustments to his calculations. The success of his formula would depend on precise timing and specific atmospheric conditions. Everything had to work perfectly. It wouldn't be long before they discovered whether his crazy idea would save lives or waste them. The first Stuka appeared as a dark speck against the clear blue sky. Within seconds, two more joined it, the formation banking sharply as the pilots identified their target. Lieutenant Winters had dispersed the convoy according to standard procedure, but in the featureless desert, the scattered vehicles remained clearly visible from above. "They've spotted us," the radio operator announced unnecessarily. The distinctive scream of diving Stukas confirmed his statement. Dr. Sutton gripped the activation lever for his system. "Not yet," he muttered to himself, watching the approaching aircraft through the dusty windscreen. Wait for them to commit. The German pilots followed their practiced attack pattern. Two aircraft circled high, maintaining visual contact with the dispersed convoy. The third dove toward the lead vehicle, aiming to destroy command and communications first. The bombing run would be followed by strafing attacks on the remaining vehicles. As the diving Stuka reached an altitude of approximately 2,000 feet, Sutton gave the order through the convoy's radio network. "Activate smoke system, now." 12 vehicles simultaneously triggered their modified equipment. The cooling component deployed first, spreading rapidly across the desert floor around each vehicle. The temperature at ground level dropped dramatically, creating a thin layer of supercooled air. 3 seconds later, the polymer solution was sprayed into this layer. The reaction was immediate and dramatic. A dense, milky white fog began forming around each equipped vehicle, spreading outward at ground level rather than rising as conventional smoke would. Within 15 seconds, the fog from adjacent vehicles merged, creating islands of concealment. After 30 seconds, these islands connected, forming a continuous bank of artificial fog approximately 1 meter high that covered nearly the entire convoy. From the air, it appeared as if portions of the desert had suddenly disappeared, replaced by what looked like natural ground fog, a phenomenon so out of place in the North African desert that the German pilots momentarily hesitated. The lead Stuka pulled out of its dive, missing its target. The pilot circled back, attempting to relocate the convoy through breaks in the spreading fog. The two observation aircraft descended, their pilots equally confused by the unexpected development. Inside the fog bank, visibility was reduced to less than 5 meters, but it remained clear enough above the 1-meter boundary layer that drivers could still navigate by looking up at the sky. The convoy vehicles regrouped, moving slowly in tight formation. Sutton monitored the fog's behavior, taking notes on its persistence and spread rate. The chemical reaction was performing better than his calculations had predicted. The ground cooling effect created a stable boundary that prevented the fog from dissipating upward, while the polymer component resisted horizontal wind dispersal. The Stukas made 3 more passes, dropping bombs on suspected vehicle locations, but the explosions landed well away from the actual convoy position. Unable to acquire visual targets and low on fuel, the German aircraft eventually departed. For 97 minutes, the fog persisted, allowing the convoy to move 15 kilometers closer to its destination. Only when the desert heat finally overcame the cooling effect did the protective screen begin to dissipate. By then, the convoy had reached an area where rocky outcroppings provided natural cover from aerial observation. All 30 vehicles reached the British lines intact, the first complete convoy to do so in over a month. Lieutenant Winters immediately reported the success to divisional headquarters, emphasizing the effectiveness of Dr. Sutton's improvised system. The chemist himself was already making notes for improvements, calculating more efficient chemical ratios and designing better deployment mechanisms. The field test had revealed both the system's potential and its limitations. The fog had worked. but it required refinement to be truly effective as a tactical tool. News of the successful convoy defence spread quickly through British forces in North Africa. General Montgomery personally requested a demonstration of Sutton's system, which was conducted on June 20, 1942, using an improved deployment mechanism. 5 days later, the first official production order was issued. The system was designated Atmospheric Obscuration Device, Type S, unofficially known as Sutton's Fog, among the troops who used it. Production facilities were established in Alexandria, with chemical components shipped from England. By August 1942, 25% of all British supply convoys in the North African theatre were equipped with the devices. German reconnaissance reports from this period reveal increasing frustration with the sudden appearance of anomalous meteorological conditions during attacks on Allied convoys. Luftwaffe commanders initially suspected some form of weather control experiment, unable to believe that the fog-like conditions were artificially generated. The technical refinement of Sutton's system continued throughout 1942. The second-generation devices reduced the chemical requirements by 30%, while increasing fog persistence time to over 2 hours. Deployment units became smaller, more reliable, and easier to install on various vehicle types. By the time of the Second Battle of El Alamein in October 1942, Sutton's Fog had evolved from an emergency convoy defense into a multi-purpose tactical system. It was used to conceal troop movements, mask artillery positions, and create false impressions of force concentration that confused German intelligence. Dr. Reginald Sutton received the George Medal for his contribution to the war effort, though much of his work remained classified until the 1970s. After developing the third-generation fog system, he was transferred back to England in early 1943 to work on chemical countermeasures against potential German gas attacks, a threat that never materialized. The scientific principles behind Sutton's fog system influenced post-war developments in several fields, from agricultural frost protection to industrial safety systems for containing toxic gas leaks. The specific chemical formula remained a military secret until 1968, when declassified versions appeared in civil defense manuals. Perhaps the most significant legacy of Sutton's work was not technological, but methodological. His success demonstrated the value of field-based innovation and the importance of allowing scientific personnel to observe actual combat conditions rather than working from theoretical requirements in distant laboratories. In his personal papers, discovered after his death in 1976, Sutton reflected on his North African experience. The desert taught me that textbook solutions rarely survive contact with reality. It was not superior chemistry that made the system work, but rather the direct observation of how the environment behaved and the willingness to adapt accordingly. From June 1942 until the conclusion of the North African campaign in May 1943, British convoy losses to air attack decreased by 67%. Supplies reached forward units more consistently, improving combat effectiveness across all operations. An estimated 3,700 transport vehicles and their irreplaceable cargoes were saved through the deployment of Sutton's system. Field Report, 7th Armoured Division, September 1942. The Type S obscuration system has fundamentally altered our logistics capabilities in theatre. What began as one chemist's desperate improvisation has become an essential component of our operational success. The simple fact remains: invisible convoys cannot be destroyed. January 1943. The North Atlantic, 300 miles west of Ireland. A convoy of 38 merchant ships ploughed through heavy seas, escorted by 6 destroyers of the Royal Navy. Sleet drove horizontally across the decks, visibility reduced to less than 200 yards in the winter storm. Captain James Hargrove stood on the bridge of the HMS Eskimo, his eyes straining to maintain visual contact with the nearest vessels. Radio silence was mandatory. German U-boats were known to triangulate on transmissions. The convoy's only defense against the submarine threat was constant vigilance and the harsh weather itself. In the captain's pocket was a sealed envelope, marked Classified, Sutton Protocol. 2 days earlier, before the convoy's departure from Liverpool, Hargrove had been briefed by a Royal Navy commander and a civilian scientist, a Dr. Phillips from the Admiralty's Department of Miscellaneous Weapons Development. "It's been adapted from the North African theatre," Phillips had explained, pointing to the specialized equipment now installed on 6 of the merchant vessels. Different chemical composition, modified for maritime conditions, but the principle remains the same. Captain Hargrove had been skeptical. "Our desert conditions and North Atlantic weather have nothing in common. The underlying physics are identical," Dr. Phillips had replied. "Temperature differential is the key. In the desert, we created an artificial cool layer over hot sand. Here, we'll generate a warm boundary layer over the cold ocean surface." Now, as the convoy entered waters known to harbour U-boat wolf packs, Hargrove considered his orders. The modified Sutton system was to be deployed only as a last resort, when submarine attack was imminent. The chemicals were in limited supply, and the Admiralty wanted operational data before committing to full-scale production. At 04:37, the ASDIC operator on the HMS Eskimo detected the distinctive acoustic signature of multiple submarine propellers. "Contact, sir. Bearing 270. Multiple contacts. Range approximately 2,000 yards and closing." Captain Hargrove made his decision. He broke radio silence with a single coded transmission. "Implement Sutton Protocol. Authenticate Victor Charlie 3. On 6 merchant vessels spaced throughout the convoy, teams of sailors activated the modified fog system. Unlike the desert version, the maritime adaptation used a different chemistry. The first component released heated seawater vapor close to the ocean's surface, while the second component, an oil-based polymer with microscopic metallic particles, was dispersed into this artificially warmed layer. The result was a dense, clinging sea fog that hugged the wavetops, extending upward approximately 5 meters, just high enough to obscure a ship's hull while leaving masts and superstructure visible to nearby escort vessels. From beneath the waves, the effect was profound. U-boat periscopes, already limited by the storm conditions, now faced an opaque barrier that prevented visual acquisition of targets. More significantly, the metallic particles in the fog disrupted the primitive radar systems that German submarines had begun to employ for surface targeting in poor visibility. The convoy adjusted course by 15 degrees, following a prearranged evasive pattern. For 3 hours, the Sutton fog persisted despite the heavy seas, gradually dissipating as the chemical components were exhausted. By then, the U-boats had lost contact, their attack opportunity gone. All 38 merchant vessels reached Liverpool with their vital war supplies intact. The maritime adaptation of Sutton's system, officially designated Protocol SM, but known informally as Phantom Fog by convoy sailors, was rapidly refined. By March 1943, production facilities in Glasgow were manufacturing sufficient quantities to equip 1 in 3 Atlantic convoys. U-boat commanders reported increasing difficulty in acquiring targets even in ideal hunting conditions. A captured German naval report dated July 1943 noted, "Unexplained meteorological anomalies continue